Having familiarized ourselves with the CP subproof procedure, we can now move on to the three-stage IP subproof procedure. One important difference between the CP and the IP subproof procedures is that the CP subproof procedure is limited in a pretty significant way. The only sentence you can derive from a CP is a conditional. A conditional of the sentence that you started the subproof with being the antecedent, and the sentence that you end the subproof with being the consequent. Of course, after you've completed the CP subproof, you're free to transform the information you've derived into a disjunction or a negated conjunction or some other construction that is equivalent to the conditional you've derived. But what if you have a situation like this one where you're asked to derive the simple sentence H from a set of three premises? The CP subproof procedure isn't really going to help you here. We can, though, use the IP sub-procedure because the IP subproof procedure can be used to derive any sentence. Before we commence with the demonstration of the IP subproof procedure, let's quickly consider the alternative when we limit ourselves to the 8 basic and 10 equivalence rules. Here we have to be careful and strategic in order to not be overwhelmed with the complexity involved for a proof like this. If we break it into stages, the first stage of this proof will be the 3-line stage, where we abandon and therefore remove the C-related information. From there, in lines 6 to 10, we strategically abandon the F-related information, and once we've accomplished that, we then transform the remaining D and E related information into the conditional E horseshoe D. Then we move to the second conditional, which is a premise, and we change the information form in which it's given so that we can do a third distribution. Here, though, we're not going to get rid of any information. Rather, we're going to end up with a conjunction of 2 disjunctions on line 16, and we're going to use both of those disjunctions. One of them will give us the conditional D horseshoe H. The other one will give us the conditional G horseshoe H. Then we'll go back to the conditional we derived from the first premise, E horseshoe D, combine it with the conditional D horseshoe H to get the conditional E horseshoe H. Then we've got, when we move to the third and final premise, the disjunction E or G, and this conditional, E horseshoe H, has an antecedent which is identical to the left disjunct in the disjunction on line 3. G horseshoe H has an antecedent which is identical to the right disjunct. So that enables us to carry out, on using lines 3, 22, and 23, a constructive dilemma to get the disjunction H or H, which by tautology will give us H. If we don't do the constructive dilemma, the proof can still be done, but it's going to be about 8 lines longer. So we'd end up with about a 33-line proof, 3 premises and 30 lines of inference. Here's a perfect situation where making use of the IP subproof procedure will enable us to conclusively prove the same thing in significantly fewer steps. Like the CP subproof procedure, the IP subproof procedure consists of the same three stages: the entry stage, then the ending stage, and finally the exit stage. We enter the IP subproof by provisionally assuming that the sentence you want to prove by IP is false. That might sound like a strange strategy to adopt, but bear with me. So, the sentence we want to eventually derive is H. So, according to the three-stage IP subproof procedure, we enter the subproof by provisionally assuming that H is false, or another way of putting it, that tilde H is true. So that's our provisional assumption. Then we proceed in the subproof and we end the IP subproof when we derive what's called a standard contradiction. A standard contradiction is a sentence with the form P and tilde P. Notice these are lowercase letters. So a standard contradiction is any conjunction of some sentence, any sentence, as the left conjunct, and that exact same sentence with a tilde in front of it as the right conjunct. Standard contradictions are sentences that are necessarily false as a result of their form or underlying logical structure. No matter the situation, both of those conjuncts can't be true simultaneously, so the standard contradiction is always false. This is a little bit different, ending the IP subproof with the standard contradiction, than ending the CP subproof, because with the CP subproof, you know exactly what sentence you have to derive to end the subproof, the consequent of the conditional you're after. With the IP subproof, we don't know exactly what sentence is going to end the subproof. In fact, in many situations, when you get near the end of the subproof, there's going to be a limited range of options available to you. You have to make a choice of a standard contradiction that follows from your original premises as well as the provisional assumption you have made to enter the subproof. Some subproofs, though, only allow of one standard contradiction. We'll begin to become familiar with what's required by doing a number of proofs. Having started off the subproof with the provisional assumption tilde H, we can now proceed in a way that we couldn't when we just limited ourselves to the original premises and the basic 8 and 10 equivalence rules. 2-4 modus tollens will give us the negation of the antecedent, which is tilde D or G. From there, we can do 5 De Morgans to get tilde D and tilde G. Now we can look at our two other premises that haven't come into play yet and see that 6 simplification will allow us to do 3-7 disjunctive syllogism to get the other disjunct namely E. From there, we can do an addition setup for a modus ponens involving the first premise. So line 9 is E or F, that's 8. Addition, line 10 is 1, 9, modus ponens, which gives us the conjunction C and D. At this point, we can start considering the question, what standard contradiction could we possibly derive from the information in the subproof? Hopefully, you will have spotted the occurrence of D-related information in line 10, 10 simp, and more D-related information in line 6, namely tilde D, so that's 6 simp. Finally, we will end the IP subproof by deriving the standard contradiction by conjunction. So 11, 12, conjunction. So notice then that conjunction is always the last step in an IP subproof. That's the step where you take some sentence, in this case it happens to be a simple sentence, but it doesn't have to be, and that exact same sentence with a tilde in front of it. So where does that leave us then? We entered the IP subproof in stage 1 by provisionally assuming that the sentence we want to prove by IP is false, namely tilde H. Then we did a modus tollens, a De Morgan's, simplification, disjunctive syllogism, addition. Notice, except for the De Morgan's, every one of our rule employments has been one of the 8 basic rules. We ended up with the standard contradiction D and tilde D. Thus, we end the subproof. We now move on to the exit stage. We exit the IP subproof by, we can skip to the second stage first here, disavowing any entitlement to use any of the information in the subproof for future lines in the proof. So, as we saw with CP then, all of the information from line 4 to line 13 hasn't been shown to be derivable from the original 3 premises alone. Rather, we temporarily supplemented the information available to us by provisionally assuming that the conclusion we're after is false, and then we made a number of inferences. When we exit the subproof, all of the information that's cordoned off by the scope lines will be evermore out of bounds. Let's consider the other aspect, though, of exiting the IP subproof. We infer that the provisional assumption, in line 3 in this case, that the conclusion we're after is false, is itself false. What's the basis for that? Here's the key idea. We're assuming that the original 3 premises are true. Suppose, in addition, we assume that tilde H is true. Well, then by modus tollens, tilde D or G is true, by De Morgan's tilde D and tilde G is true, and so on until we end up at line 13 with the inference that the conjunction D and tilde D must be true. But D and tilde D can't be true, because D and tilde D is a standard contradiction. A sentence that has a form or underlying logical structure such that it's necessarily false. So, assuming that the three original premises are true, if we assume that tilde H is true and end up being committed to the claim that a standard contradiction is also true, what's the only logical conclusion to draw from that? The only logical conclusion to draw from that is that, given that our premises are true, if the provisional assumption of tilde H commits us to a standard contradiction, which is necessarily false, then tilde H must be false. There's no other logical way of looking at it. The standard contradiction in line 13 is necessarily false, but the provisional assumption that tilde H is true committed us to this necessarily false claim. Therefore, we're entitled to conclude, and this is what we've shown in the subproof, given that the original premises are true, if we assume that tilde H is true, then we're going to be committed to asserting that the standard contradiction D and tilde D is also true, which it can't be because it's necessarily false. Therefore, we're justified in concluding that tilde H must itself be false, which is to say that H is true. So that's been proven in lines 4 to 13 by indirect proof. Another way of looking at it, we have proven that the conclusion H is true, not directly. Here's a direct proof that H is true, given that these three premises are true. So we've got this sequence of valid rule employments. Here's an indirect proof that H must be true, given that these three premises are true. Let's provisionally assume that tilde H is true. Or another way of putting it, let's provisionally assume that H is false. Then we end up in an impossible situation, committed to the claim that this sentence, which can't possibly be true, must be true. Therefore, tilde H can't possibly be true, because if it was true, then D and tilde D would also be true. But D and tilde D can't be true, given that these three premises are true. Therefore, tilde H can't be true. That's what we've proven in the subproof. Another way of putting that is to say we have indirectly proven that if these three premises are true, then H must be true, by proving that tilde H, H's negation, can't possibly be true because it leads to a standard contradiction. The IP subproof procedure is also sometimes called by the Latin phrase reductio ad absurdum, which just means reduce to absurdity or impossibility. Notice though, what's being reduced to absurdity or impossibility is not the sentence we're ultimately trying to prove by IP or reductio ad absurdum. Rather, we're reducing the denial or negation of the position we're ultimately trying to prove to absurdity when we use the IP procedure. What we're doing is demonstrating, well, look, it's not possible for my position to be false, because if it were false, then impossible things would have to exist or obtain. Namely, a particular standard contradiction which can't possibly be true would have to be true. Since standard contradictions can't possibly be true, the provisional assumption that my position is false, which forces that upon us, can't possibly be true either. That is a proof, an indirect proof, that the position I'm trying to convince you of must be true, because its negation can't be true. Here's another example of an argument where an IP will be useful. This argument is going to allow us to demonstrate the other version of IP. You don't really need two versions, but most textbooks have both options as far as the IP subproof procedure goes. The idea is, if you want to derive an unnegated sentence, as we did in the last proof, H, let's say, then in the IP subproof, you add a tilde and prove a standard contradiction in the IP subproof, and conclude that your provisional assumption without the tilde added is proven. In the case of wanting to prove a negation, as in this case, from the two premises, we want to conclude that the negated conjunction follows. Instead of adding another tilde, so that our provisional assumption is tilde tilde A and tilde C, we could just remove the tilde so that our provisional assumption is the conjunction A and tilde C. So it turns out the two different versions of IP aren't really any different, and having two different versions just saves you from having to do an additional double negation step. So we can start off the IP here, instead of with tilde tilde A and tilde C, from which we then have to do 3 double negation to get A and tilde C, and proceed on from there. We can just start the subproof with A and tilde C is our provisional assumption. If we can demonstrate that, given that the two premises are true, if the provisional assumption A and tilde C forces us to a standard contradiction, we will then have proven that the conjunction A and tilde C can't be true, which is an indirect way of proving this sentence, the negation of A and tilde C. So we start off with our provisional assumption. Here, the first simplification, 3 simp, gives us the antecedent of the second premise. So 2, 4, modus ponens will give us D. Now we've got the antecedent of the first premise, 1, 5 modus ponens will give us tilde A or B. Now, we still have to get a standard contradiction. Here, I'll simplify the other conjunct from our provisional assumption, 3 simp. But then, instead of doing a De Morgan's on line 6 to get tilde A and tilde B, and then simplifying tilde A and then putting A and tilde A into a conjunction, which would be a correct way of doing it, but just to illustrate, we could also do it this way. Having A, we can do 7 addition to get A or B, so that we can end the IP subproof on line 9 with the standard contradiction A or B and tilde A or B. That's a standard contradiction as well. Any sentence as the left conjunct, that exact same sentence with the tilde in front of it, as the right conjunct. So that's 6, 8, conj. From that, we infer by IP that it's not the case that A and tilde C is true, given that our original premises are true. That's what we've proven in lines 3 to 9 by IP. With this next proof, I'll illustrate a situation which is reasonably common. Here we've got a 3-premise argument with a conditional for a conclusion. So suppose we start off doing a CP. That is to say, we provisionally assume that in addition to our 3 original premises, A is true. Then all we have to do is prove B. Now, looking at our information, it's not immediately available how we can derive B from our original 3 premises plus the provisional assumption A. So we might decide to do an IP subproof inside the CP subproof. Remember, what we're after to finish the proof is the consequent of the conditional B. So for the IP inside the CP subproof, we will provisionally assume that B is false. Then all we have to do is derive a standard contradiction that will show that given that the original 3 premises in A are true, tilde B can't be true, so B must be true, and then we can exit the initial subproof with the CP. So, now that we've got our original 3 premises, plus the CP provisional assumption, and the IP provisional assumption, 2-5 disjunctive syllogism will give us tilde S. 3-6 disjunctive syllogism again will give us R. 1-7 modus ponens will give us tilde A and T. What do we need to end the IP subproof? we need a standard contradiction. We've got the provisional assumption A in the original CP subproof, so all we have to do is 8 simplification, and then in line 10, as always, we will end the IP subproof with a conjunction A and tilde A, so that's 4, 9 conjunction. So again, given that the original 3 premises are true, if A is true, then tilde B can't be true, because if it were, then the standard contradiction A and tilde A would have to be true. So that innermost subproof is a proof that if the original premises plus A are true, then tilde B can't be true, which means B must be true. 5 to 10 IP gives us B. Now we exit the original CP subproof, having proven in lines 4 to 11 by CP that if the original premises are true, then if A is true, then B must be true, which shows that if the original premises are true, then the conditional A horseshoe B must be true. At this point, we can go back to assignment 8, exercise 413, question 14. Here we've got what appears to be a reasonably simple proof. We've got 2 conditionals, and from that we're asked to derive a third conditional. If we confine ourselves to the 8 basic and 10 equivalence rules, however, this seemingly simple proof is going to turn out to be a little bit tricky. So we've got these 2 conditionals. How do we proceed if we're not using subproof rules to derive this third conditional? This is a proof where, when you're confined to the 8 basic and 10 equivalence rules, the strategy of backwards planning is pretty much essential. So ultimately, we want to end up with this conditional. If A or C, then B or D. How are we going to derive that conditional, given our 2 premises? It's not at all clear how we can deduce this conditional from these 2 premises. What this should tell us is that there's got to be a distribution involved. Once we realize that there's got to be a distribution involved, we can then ask ourselves, how would this conditional come from a distribution? The answer would be, well, it would have to come by implication from a disjunction. So the disjunction would have to be tilde A or C, or B or D. Then we can ask ourselves, how are we going to be able to get this disjunction from a distribution? Well, getting this disjunction that has a negated disjunction as its left disjunct would have to come from De Morgan's, from this sentence, tilde A and tilde C, or B or D. If we could just get this sentence, Then by doing a De Morgan's on the left-hand side and then an implication, we could get the assigned conclusion. How are we going to get this sentence? At this point, hopefully, you're familiar enough with distribution that you can see how this is going to work. If a distribution is involved, we get this sentence by commutation from this disjunction. And this is a sentence that finally fits the distribution template. If you look at the bottom part of the distribution rule on page 13 of the handout notes, what we're after is a disjunction of this form, P or Q and R, where P is the disjunction B or D, Q is tilde A, R is tilde C. We can get that from the conjunction P or Q and P or R. So we'll get this by distribution if we could only get the following conjunction. B or D or tilde A and B or D or tilde C. So how are we going to get this conjunction? Answer, we'll get it using the conjunction rule. So we'll have to get each of these conjuncts separately. Can we get each of these conjuncts separately from our two premises? If we can, then we can put them together by conjunction, do a distribution to get this disjunction, do a commutation, De Morgan's, and implication to get our assigned conclusion. Well, let's start with the left one. B or D or tilde A. We can get this one by doing one implication, which will give us tilde A or B. Now, here we've got tilde A and we've got B. We need to introduce D-related information, so we will do a strategic addition step on line 3 to get tilde A or B or D. Then we will use the association rule to get tilde A or, and these two go together, B or D. Finally, we will do a commutation on the entire line to get B or D or tilde A. So we've got the first conjunct in the conjunction we need to get the conclusion through this series of steps. Now we'll focus on the second premise and the task of getting this disjunction, which is the right conjunct. So again, tilde C or D is going to be 2 implication. Now, tilde C or D, and we want to introduce B-related information here, or B is going to be 7 addition. Now, we will do 8 association to give us tilde C or D or B. Then we'll have to do a commutation on part of line 9, and then a second commutation on the entire line 10. So the commutation on line 10 will give us tilde C, or, not B or B, but B or D. Then the commutation on the entire line will give us B or D or tilde C. So that's the second of the two conjuncts that we need. So having planned this out in advance, then line 12 of the proof will just be B or D or tilde A and B or D or tilde C, which is just 6, 11 conjunction. Now we do a distribution on line 12 to get B or D or tilde A and tilde C. Here we could do the commutation first, or the De Morgan on part of the line first. Doesn't matter. I'll do the commutation first to get tilde A and tilde C or B or D. So that's 13 commutation. Then I'll do the De Morgans to get tilde A or C or B or D. Oh, didn't quite leave myself enough room. I'll try to force the last two lines of the proof in there. So now we just do, oh, there's just one line left. We do 15 implication to get A or C horseshoe B or D. So not a super long proof, only 14 lines of inference, but a pretty tricky proof. A proof which requires fairly intricate strategic planning. We can now contrast this procedure, which is necessary if we confine ourselves to the 8 basic and 10 equivalence rules, to this alternative procedure if we can use subproof rules. Since the sentence we're after for the conclusion is a conditional, we'll do a CP, provisionally assuming the antecedent of the conditional we're after, namely the disjunction A or C, so that's our provisional assumption. Now, hopefully you notice this, 1, 2, 3, constructive dilemma will give us the disjunction B or D, which is the sentence we need to end the CP subproof, so that line 5 will be 3, 4 CP, giving us A or C horseshoe B or D. So this is probably the most extreme situation of availing ourselves of the subproof procedure makes the proof substantially shorter and substantially easier than if we were to limit ourselves to the 8 basic and 10 equivalence rules. At this point, I'd be remiss if I didn't give you at least a couple of concrete examples of proofs where it's not a good idea to do a subproof and you're better off just limiting yourself to the 8 basic and 10 equivalence rules. A good example is the following proof, which comes from exercise 4.8. Here we've got a disjunctive syllogism opportunity right off the bat. 1,3 disjunctive syllogism will give us tilde A. Now, and this is the part of the proof that requires some familiarity with the rules, we've got tilde C as the consequent of a conditional, so all we need to do is get the antecedent, then we can derive tilde C by modus ponens. The antecedent is the negated conjunction, tilde, and then in brackets, A and tilde B. We've got tilde A, so we have to do a strategic addition step. The strategic addition step we want to do is tilde A or tilde B. So that's for addition. Notice there's no requirement that we do tilde A or B and then do a separate double negation step. The addition rule allows you to add any sentence. It doesn't have to be a simple one. Being familiar with the rules, we do the correct addition step so that 5 De Morgans will then give us tilde, and then we remove a tilde from both sides and change the or to an and to get A and tilde B, so that 2,6 modus ponens gives us the conclusion. In the proof, we did a disjunctive syllogism, an addition, a modus ponens, 3 basic rules, and a De Morgan's step. So a little bit of figuring out, a little bit of familiarity with the rules is required to do the right addition, but other than that, a fairly straightforward proof. Now, suppose, looking at this same information, we decided to do an IP. Since the sentence is a negation, the CP isn't going to work here. So, we provisionally assume C, then we just have to derive a standard contradiction, and that will be an indirect proof that if these 3 premises are true, C can't in addition be true, therefore tilde C must be true. So having made that provisional assumption, we have to do a double negation step to get tilde C, so that's 4 double negation. Now, 2,5 modus tollens will give us tilde A and tilde B. Then we can do a De Morgan's, or sorry, not a De Morgan's, just a double negation on line 6 to remove the 2 tildes and the brackets necessary to indicate that the innermost tilde ranges over the entire conjunction to get A and tilde b. Now, we have to do the disjunctive syllogism that we started this proof off with, because we are using the same information. So 1,3 disjunctive syllogism gives us tilde a. So we snap off A7 simp. Then, as always, we end the IP subproof with a conjunction step, 8, 9 conjunction, to derive the standard contradiction. So we exit the IP subproof 4 to 10 IP, having proven that if these three premises are true, then C can't be true, which is an indirect proof that tilde C must be true. Notice this proof is at least as complicated as this one over here, but instead of requiring 5 inference steps, it requires 8. So here's a situation where clearly the IP subproof procedure isn't going to make things easier. So remember, the rule here is the longer and more complicated a proof is, the more likely that doing a subproof and perhaps multiple subproofs will make the proof shorter and easier. The shorter and simpler a proof is, though, the less likely that a subproof is going to make the procedure shorter and easier, as this example illustrates. Here's another example of a proof that's kind of complicated. You might recall this proof from lecture 9. Here we've got P, Q, R, T, and W related information. We've got multiple occurrences of Q related information, one in every premise, and we're asked to derive the conclusion P. This involves some careful consideration in order to set up the two separate Q stages. So we start off with an implication, double negation, followed by an implication back the other way, so that we can get the Q and R related information in line 2 to link with the Q and R related information in line 3. Then when we do an equivalence and select the appropriate conjunct, we end up with T related information in a Q and R stage. Then we introduce W by addition. Double De Morgan sets us up for a disjunctive syllogism where we get the second bit of Q related information. We do the equivalence on the first premise, so that we finally end up with P related information as the conclusion. It seems as if this is the kind of proof where doing a subproof might be worth a try, but as we'll see, that's not likely going to be the case. So we start off, since the conclusion is P, by provisionally assuming that that conclusion is false, then looking for a standard contradiction. The key tip-off here is when we introduce tilde P into the mix, there's no real advantage to be gained by having this additional sentence. We can do an equivalence on line 1 to get P horseshoe tilde Q and tilde Q, horseshoe P. Since we've got tilde P, we snap off the right hand side, tilde Q, horseshoe P, that's 6, simp, so that we can do a modus tollens, 5, 7, modus tollens to get tilde tilde Q. Now, tilde tilde Q is useful for line 4. It sets us up straight away into a disjunctive syllogism for 8. Disjunctive syllogism gives us tilde T or W, which we can then do a De Morgan's to, 9 De Morgan's. Then, since we've got T-related information in line 3, we will just leave the right conjunct of line 10, tilde T, 10 simp. Then, as we did previously, we'll do the equivalence and then select the version that'll allow us to do a modus tollens. So, T, horseshoe, tilde, Q, and tilde R, and tilde Q and R, horseshoe T. So that's going to be 1 equiv. Once again, it's the right-hand version that's going to be of use to us, given that we've got tilde T. So tilde Q and tilde R. We'll have to make sure the tilde is there. Horseshoe T is going to be 12 simp, so that 14 is going to give us tilde tilde Q and tilde R. Then we can do a double negation to get Q and tilde R. So that's 11, 13 modus tollens for line 14, and then 15 is 14 double negation. Now, we've got tilde tilde Q on line 8, so there's no Q-related standard contradiction. What we have to do is remove tilde R, so that's 15 simp. Then 2, 16 modus tollens will give us tilde Q. So we could snap off the Q from line 15, but notice on line 8 we've already got tilde tilde Q, so 8, 17 conj will give us tilde Q and tilde tilde Q, which is a standard contradiction where lowercase p is tilde Q and tilde lowercase p is tilde tilde Q. So finally, 5 to 18 IP gives us P. This is hardly a simpler proof than the one over here. It ends up being 19 lines instead of 16. Good example of the concrete fact that even though with a proof like this, I would say it's more likely that doing a subproof is going to make the proof shorter and easier, but there's no guarantee of this. The key tip-off, though, that an IP subproof is probably not going to be too helpful is the fact that the additional information we get from the provisional assumption that starts the subproof doesn't really give us any sort of an advantage. In any case, you always have to keep that in mind. Sometimes you will get substantial advantage by doing the subproof. Sometimes, even though it's likely, in the abstract, it won't turn out that way. By and large, though, just to remind you, the longer and more complicated a proof is, the more likely, though there's no guarantee of this, the more likely that a subproof strategy will produce a shorter and simpler solution.